Hi, welcome back. We don't need this hello world. We're rustaceans at this point. We don't need silly hello worlds anymore. We're getting into the good stuff, right? Today we're going to be touching on iterators and closures. I'm just going to go ahead and get right into it by first taking a look at this shirt giveaway logic from the textbook. So I'm just going to yoink it over here and we'll go through it real quick. So first of all, we have an enumerable shirt color, red or blue, and we derive these traits, which we're going to use later. We have a inventory made up of vectors of the shirt color. So on inventory, we're going to implement this giveaway method, and that's going to take in a user preference, and based on our inventory, if they do give us some shirt color, then we're just going to return that. Otherwise, we're going to, and that's what this unwrap or else does right here, is we're going to unwrap Arnold thinks so as well. We're going to unwrap this shirt color from the sum, if it does indeed exist. Otherwise, we're going to, if it's a none variant on option, Arnold, you're getting booted out. I'm sorry, bud. Yeah. Cat antics aside, we're going to, in case of the none option, execute this closure right here. And again, a closure is just a inline function at this point, but it can also take in environments from its variables. So as you can see here, self isn't declared within our arguments here. That's what these pipes are, is we put in our args here, and we'll go over that later, but we're grabbing self from the environment or the scope of this function. So self is visible here, self.mostStocked. And all this is going to do here is count the number of shirts that are in the inventory and return the shirt that is most stocked. So this is a little example down here. We created an inventory with a couple shirt colors, and one user's preference is red, and giveaway for red is going to be red for this print statement here. And now, since user 2 doesn't have a preference, we're going to unwrap or else. We're going to execute the else part, most stocked. And in this case, it's going to be the shirt color blue, because we have two blue shirt colors and one red shirt color. So I'll go ahead and do a cargo run real quick after I save. And as you can see, that makes sense at this point. Now that's out of the way, let's go ahead and nuke this real quick. Start over from scratch. And we're gonna write our own closure now at this point. So we're gonna call this expensive closure. Let expensive closure, and we're gonna basically sleep for 2 seconds. And this is gonna look fairly familiar to a function at this point. So we're gonna take in a U32, if I can type, and we're gonna return a U32. And we're going to print slowly calculating. And we're going to return num. And this is how you define a closure as a variable. And note this time, most of the time we don't need to annotate our input parameters, because the compiler is able to infer what type these input parameters should be if we're passing this into a function, right? But anywho, if we wanted to call a closure by itself, we could just do expensive closure and pass in our number 5, and I'll do a cargo run again. So we'll go over threads later. but this is a good introduction into how we would sleep. Yay, we got 5 after slowly calculating. And this is a good example of why we would use a closure in like a separate thread. If we had an expensive operation, we could assign that to a different thread, but that's for a different video. And we very well could actually take off these type annotations and say it could be what? Like any type. We don't really specify return or input type. It infers that it should be, in this case, a signed 32-bit because that's the default for if we just write out an integer, actual integer in our code, it's going to default to I32. So we're able to still run this. But now if we try doing something like let y equal expense of closure with the character C, since we've already inferred that it should be a 32-bit signed integer, the compiler is going to complain at this, and it's going to say that, hey, we called it with this, so we expect future calls to it to be of the same type. And like how we saw in our shirt example, we can use variables outside of our closure. So we didn't actually define list in here, we grabbed it from our environment. So just a quick example, I'll do another cargo run. As you can see, we can call it before, defining the closure, before calling it, from calling it, and afterwards. That all works fine and dandy because we're using a immutable reference here. Basically, Rust is going to use the least amount of permissions required for our closure. Since we only need an immutable reference to print our list, we get exactly that in our closure. And we also haven't covered this a lot, but by using the : formatting within a print or formatted string, we are telling the formatted string to use the debug trait on whatever our variable is instead of the display trait, because vector doesn't have the display trait implemented by default, which is what our print line macros would have used if we didn't specify : Now if we wanted to go the next level up, we could do something like this. I call this borrows mutably because guess what? It borrows list mutably, and we need to also specify that the closure is going to be a mutable type instead of just a regular one. Otherwise the compiler is going to bug out on us and say, hey, like you're trying to borrow this reference mutably, what are you doing? So we're going to head and let that stay as mute, and if we run this now, it can do exactly what you think it would do. It's going to push forward to the vector. And finally, if we wanted the closure to take ownership, I've gone ahead and imported thread, and we're going to make a new thread. And again, we're going to talk about threads later, but making a new thread, and we're basically saying with this move keyword here that anything that's defined within our closure, it should take ownership. And we're doing this with a thread because otherwise we're going to run into a race condition, right? If we are able to mutate list within a thread and it's still available in the main thread, then that's a problem, right? So move basically allows us to capture and take ownership of any environment variable specified. And just for sanity's sake, let's do a quick cargo run from thread 123. Everything about closures is relatively straightforward at this point now. So let's take it up like a half notch. Basically, we're going to have 3 defined behaviors for our closures that we just went over. We either affect nothing in our environment of the closure, which we did when we printed out a list, or we affect something in the environment via mutable reference, which we did when we did our closure that pushed 4 to the list, or finally we can take full ownership of a variable, which is what we did right here. These closures implement fn, which is immutable or no references within the closure, fn mute for mutable references, or fn once, which this is in the case that we take full ownership. fn and fn mute, and these are, I'll just write them, fn mute, and fn once. fn and fn mute closures can be called more than once since they don't take ownership, while, you guessed it, fn once can only be called once because it takes ownership of something that it's using. In addition, fn inherits fn mute, which inherits fn once. So basically, if we're defining some sort of function here and we take in a closure that is an fn once, it can be either fn once, fn mute, or fn. If it's an fn mute, it could be fn mute or fn. And if it's a fn, that basically means this can't mutate anything, right? Makes sense at this point. In practice, this is what our unwrapper else looks like, and again, it's implemented on the option type, and this is exactly what it does in the standard library. So takes in self, it takes in a closure of type f, and it returns our type t, which is wrapped within the sum variant. And we're saying here that f can be a at least callable once. So it can be either something that takes ownership, or mutable reference, or immutable references. It doesn't really care. And it returns a type t. So if we actually do have some value, we're going to just spit it out. Otherwise, we run the closure, and that's it. Now that we got that sorted out, let's take a look at another method that is implemented in our standard library, more specifically on lists, the sort by key method, which, you guessed it, takes in an element and sorts it by some constraint that's sortable. Now pause the video real quick and see if you can guess what trait the sort by key method takes for a closure. Either fn, fn mute, or fn once. As a hint, we try to be as least restrictive as possible in our closure definitions. If you guessed fn mute, you're in luck. Sort by key can't be called once since it's called for each element in the list, which makes sense because we're sorting the list. We're going through each element in the list. But we also don't really care if it mutates the environment or not. So the Rust developer said that our closures can be an fn mute. Although what we passed in the closure didn't affect its environment, it was technically an fn because we weren't affecting anything outside of the environment. But since fn inherits fn mute, then it all works fine and peachy. That makes sense? Now let's say we want to get our push operations from each time that we push and do something that mutates our environment from a sort by key. So right here we have sort operations.push value. So we're pushing value onto sort operations, and we're returning the width, which is what the sort by key method uses to sort our list. Now, if I save this isn't going to compile, and I would implore you to pause the video real quick and see what's wrong with here. If you guessed it's because we made it into an fn once closure, you're right. We are indeed moving ownership of value into our sort operations vector by referencing it like so. So this is an fn once because we need the ownership of, or the compiler is going to infer that we want ownership of value if we're pushing it to sort operations. We can fix this by instead pushing references to sort operations. Okay, that's it for closures. In summary, closures allow us to define inline functions, or in other words, place them inside of arguments to other functions. We saw how closures can mutate variables outside of their body and can either inherit the fn mute, or the fn once traits. And without ado, let's move on to the second part of this video and go over iterators real quick. Iterators are just a fancy way to loop over items in a collection of some sort. They work kind of like for loops and actually work in tandem with them, but allow us to write a bit more safe code as opposed to for loop with manual variables. We've actually been using iterables without knowing it. So for example, if we had my vec equals vec with 1, 2, 3, by doing for v in my vec, we're actually using iterable by doing this. We're calling the into iter method. It's the same thing as into iter on my vec to get the iterable type, and then we actually loop over the iterable to consume up our my vec. We're quote unquote consuming it because we have full ownership of v, and therefore goes out of scope for each iteration of the loop. If we still wanted to use my vec after iterating over it, we could do something like my vec iter is going to equal my vec dot iter, and then for v in my vec iter, then as you can see, we're getting a reference and we can loop over it. I'll just do cargo run real quick, just for fun. 1, 2, 3. What makes an iterator is just the fact that it implements, you guessed it, the iterator trait. This trait calls for only a single method to be implemented on it, next. Next is just a method that gets the next item in the list or iterable or whatever it is and spits it out for us, and increments any internal state of the iterator to make sure we're able to get even the next value. We can make our own iterator just to nail the point home. We'll iterate through the Fibonacci sequence since that's always a fun comp sci problem to tackle. Pause the video real quick and see if you can create an iterator for the Fibonacci sequence up to 8 using the iterator trait, and we need to implement what's a good thing here. I'll just do squirrely, sure. It needs to implement this next method on it. So I went ahead and created a struct fibgen, and I created a constructor for our fibgen here, which takes the initial value of the Fibonacci sequence, 0 and 1, and then we're implementing the iterator trait. And again, this type item stuff we'll get into later. Sorry if you had a hard time with that if you're trying to implement this yourself. And then we implement our next method here, which takes a mutable reference to self because we need to update this internal counters or of what our last fib sequence was. And we're returning an option here because we need to eventually know when we've reached the end of our iterable. So we're going to go ahead and say our next sum is the last 2. If it's greater than 8, then we return none, and then we update our last values with what we just calculated, and we return our wrapped new sum, uh, sum, not some, our n2 value here in sum. And we can go ahead here and just do another cargo run. And as you'll see, 1, 2, 3, 5, 8. We're missing the first 0, 1 from here, but that's besides the point. I just wanted to quickly show how iterators work. We also have the concept of these consuming adapters. They're pretty straightforward. They're methods that are exposed to us through the iterator that uses up the iterator. Since our unsigned 8-bit integer here implements the sum trait, we also get exposed the sum method for the iterable. So we could do something like let sum equal fib.sum, and we could go ahead and print out our sum. Go ahead and do cargo run. Whoops, and we need to specify this as an unsigned 8-bit integer because we can't infer that from here. And you can do the math if you really wanted to, but I promise you that 1, 2, 3, 5, 8, that all adds up to 19. Another example of a consuming adapter we've seen is the collect method. So we could do something like let my vec be a vec of, I don't think we need to specify u8 here, but I'm going to go ahead and do it anyways. This is going to equal fib.collect, and we could print, we're going to do a debug statement of my vec. And just like that, we now have a vector collection of our Fibonacci sequence. Iterator adapters, on the other hand, transform our iterable into another iterable. We can do something like this. For f in fib.map, use a closure here, x plus 1, and we print out our f. You can guess what's going to happen here, right? We're going to do plus 1 for every element within the fib sequence. So if I do cargo run here, it's all added up by 1. Do know that an iterable by itself, we kind of touched on this briefly when we did actually this right here. An iterable by itself does not do anything until we consume it, either with a for loop or with a consuming adapter of some sort. But that's it for this video. In summary, we went over how closures are inline functions and have the ability to modify their environment. They can inherit fn mute, or fn once, depending on if they mutate or take ownership of values outside of their body. We also saw how iterators work and went over consuming adapters and regular adapters like map. Next up, we'll finally talk about the box type and smart pointers. So, exciting video. I'll see you in the next one.